So, again, the properties of vector space. Now, I stated these a little more fully last time. I'm just going to give you the flavor this time. Go back to the video if you haven't seen it. I know you're preparing for a quiz, but you want to keep up with this stuff because you don't want to come in Thursday not knowing anything about vector spaces. Okay? You got to know some stuff because we're going to go on from there. You'll be lost. So you got 2 more days that you didn't know you have to prepare for the major quiz. Spend some time doing what I'm asking you to do for your assignment because it's going to be due Thursday. Okay? Okay. So a vector space consists of vectors. What are vectors? Well, not always what you think. I mean, we've seen them as arrows. We've seen them as columns of numbers, right? Those are the 2 basic ways we've seen vectors. And we can visualize them in 2 or 3 dimensional or 1-dimensional space. You know, just arrows that either go this way or this way, right? Okay? Now, a vector is anything that has the same properties that those things do. Because those things all have the same properties. Now, we state those properties, and there are anywhere from 8 to 12 of them, depending on how compactly we want to state it. Okay? I don't remember how many statements your book has. Nobody is going to remember all those statements. Okay? But everybody should be able to prove all those statements about a vector space. Okay? Unrealistic to ask people that have never been asked to memorize anything to memorize much of anything. So we work out the sense of these things. Okay? So, but the 4 things I'm giving you right here, you got to know. These are the things, first things you test when you're testing whether you have a vector space. There is a whole list of other things, anywhere from 4 to 8 more. Okay? And they're simple. Usually they're simple. These are the 4 that usually cause things not to be vector spaces. So that's why we're starting with a subset of the properties. Okay? So we can at least exclude certain things from being vector spaces. And then I can say, okay, this is going to end up being a vector space, but we haven't really proven it yet. Okay? So, what are some things you could add 2 of to get another one? How about 2 continuous functions? You could add 2 continuous functions and get a continuous function, right? Continuous on some interval. Okay? Okay? Add 2 numbers. Well, it depends what kind of numbers. Okay? But if it's integers, if you add 2 integers, you get an integer, right? If you add 2 whole numbers, you get a whole number, right? Okay? If you add 2 rational numbers, you get a rational number. If you add 2 irrational numbers, do you get an irrational number? No. Give me an example of an irrational number. What'd you say?
No,
I saw how your lips moved, and I thought it might have been it, and it might have just been you're having dental problems. I don't know. It looked like you might have said pie, which would be a good example.
Yeah,
that's
pie.
kind of. I'm not a great lip reader, but it sure looked like a. You know, it didn't look like that. Not nearly that bad. Okay. So you know, well, I'll give you 2 irrational numbers that add up to pi. Ready?
Mm-hmm.
Pi minus 1 and pi plus 1. Okay?
That works.
But that adds up to pi. Now, can you give me 2 irrational numbers that add up to a rational number?
1 minus pi.
And?
1 plus.
Okay, 1 minus pi and 1 plus pi would work, or just 1 minus pi and pi.
Yeah.
Okay? So irrational numbers can add up to numbers that aren't irrational. So irrational numbers are not even a candidate for a vector space. Okay? Now all real numbers, yeah, any 2 real numbers will add up to a real number. Any 2 complex numbers will add up to a complex number, right? Real numbers, of course, are a subset of the complex numbers. Okay? So there are lots of things we could add. Anything from different types of numbers to functions to columns of 78 numbers, but we already understand those as vectors, right? Okay, even though I don't think I've asked anything over 77, have I? No. Okay, so add 2, we get 1 of them, right? Ain't true for irrational numbers, but it's true for about everything else that I mentioned. Okay? Now, which property I want to talk about next? There's an additive identity, and I explained last time what that is. It's like 0 in the real numbers. If you add 0 to a number, you get that number. It doesn't change the number you add it to, right? Well, if you got an arrow, what arrow do you add to this to get the 0 arrow? The one that's equal and opposite, right? So arrows do that, right?
Mm-hmm.
Columns of numbers, just change all their signs and add them and you get the 0 column, right?
Mm-hmm.
Okay? Matrices. Matrices form a vector, they end up forming a vector space. If you add two 5x5 matrices, what do you get? You get a 5x5 matrix, right? What would you add to a 5x5 matrix to get the same matrix back? The 0 matrix. Okay? And then additive inverses. Everybody's got an additive inverse. Okay? What's an additive inverse? It's what you add to the number to get 0, and I think that's what I was just talking about. I kind of morphed over into that when I said you change all the signs and add them up, you get 0, right? Okay? So I kind of used the wrong example on that one, but I think everybody understands me. Okay. So everybody got an additive inverse, okay? That means every element of your set has an additive inverse, right?
Mm-hmm.
So if you got a set of vectors, okay, add 2, you're going to get 1.
Mm-hmm.
Okay, that's closure. Set is closed. You can't get out of the set by adding 2 members of the set. Okay? This is the identity property, this is the inverse property, so I don't really have to write down anything. Okay? Then, multiply one of them by a number, you get one of them. Okay? It's another closure property. Okay? Now I say number, this extends to an element of a field. So if you ever get to the point where you do vector spaces over fields, which you probably won't, okay, but might, they're engineering disciplines, we got to know that, okay? But, yeah, they're kind of specialized, okay? And I can't even think of one right now, but because I'm not thinking right now, okay? Make sense? So there's, it's not always just a number, but if it's a number, remember, it could be any set of numbers that forms a field, right? Okay? And, various sets, maybe rational numbers form a field, okay? Whole numbers, yeah. We're not going to get the field properties, okay? Some of those things do constitute a field, some of them constitute a ring, You don't need to know that. So for our purposes, but I want to issue this disclaimer, it's not always just a number. It could be a real or a complex number. Okay, your field would be the field of real numbers or the field of complex numbers in this class. And we're not going to deal with complex in a little while. Okay? Okay, so there are 4 properties. Now the numbers of these properties, I'll probably use different numbers because I probably won't remember how I numbered these, but maybe I will. Okay, so when I refer to property 1, I'll have to have a list of what I mean by 1, 2, 3, and 4, right? There's not a universal list. Okay. So, well, those are the properties of a set of vectors. Those are 4 of the properties of a vector space. You got to have a set of vectors that satisfies these conditions. And you got to have a field, which is implicitly, right now, real numbers, okay? Because if you don't have a field, you don't have a field to multiply these things by. You don't have numbers to multiply by, okay? And of course, we know what it means to multiply any of the vectors that we've actually used by a number, right? If I want to multiply this vector by 5, I just make it 5 times as long, don't change its direction, right? If I'm using an arrow, if I want to multiply a column of numbers by 5, well, that's obvious, right? If I want to multiply a matrix by 5, well, that's right. And the determinant becomes 5 to the n times big, doesn't it? If it's a square matrix. Okay.